Hello, today I'm going to do a problem on spring forces. So this is a sort of simple problem, but it has a sneaky little piece where you have to think about the nature of springs. So it's a good sample problem for us to try. The problem is a 9.5 kilogram sculpture is suspended vertically between two springs. The top spring has a spring constant of 80 newtons per meter, and the bottom spring has a spring constant of 30 newtons per meter. The bottom spring is stretched 40 centimeters. How much has the top spring stretched by? All right, our process. Draw a picture. We have a sculpture suspended vertically between two springs. So we've got a spring here, and then sculpture, very exciting sculpture, right? Between another spring. There is my picture, my knowns. The sculpture has a mass of 9.5 kilograms, and kilograms mass. The top, I'm going to call this one, spring 2. The top spring has a spring constant of 80 newtons per meter, K1. So the spring constant of spring 1 is 80 newtons per meter, and spring 2 had a spring constant of 30, K2 is 30 newtons per meter. The bottom spring is stretched 40 centimeters, so delta X for the bottom spring is 40 centimeters, and now I'm going to convert that immediately so I don't mess myself up, convert it to meters. We want to know how much has the top spring stretched by, delta X1. All right, there's my setup. We have spring, sculpture, spring. We know the mass of the sculpture, the two spring constants, how much we know this one, and then we're looking for the stretch of that one. I'm going to do the forces on the sculpture. That's the appropriate object. In this case, I don't know anything about the springs in terms of their mass or something, so if I did a force diagram on the springs, it would be a little weird. So this is the thing I'm going to do the force diagram for. All right, it's got the force of gravity, our weight, straight down. Spring 1 is pulling up, so F spring 1. And then here's the sneaky part about this spring. I can imagine two different scenarios. I can imagine that this sculpture is pulling up on the spring, in which case the spring force is down, pulling down on the sculpture. Sculpture pulls up on spring, spring pulls down on sculpture. The other case is maybe this sculpture is kind of sitting on the spring, and so it's pushing down, in which case the sculpture is pushing up. How do we know which one of those is true? Well, we are told, and this is a very subtle point, the bottom spring is stretched 40 centimeters. This spring is not compressed, it's stretched. Springs always want to go back to their equilibrium point, so this spring is trying to go back down. So it's pulling down on the sculpture. So I'm going to put a second downward force from the second spring, and that is all I've got for my force diagram. We've got the top spring pulling up on it, the bottom spring pulling down on it, and the earth pulling down on it. There we go. This is going to be pretty easy. It's holding still, so there's no acceleration, which means X is going to be balanced, Y is going to be balanced. And my XY chart is kind of boring because there's nothing here. There are no horizontal forces. I have a positive spring 1 force, I have a negative spring 2 force, and a negative weight, mg. Okay, add up all the forces in the X direction, set them to 0. Nothing there. Add up all the forces in the Y direction, set them equal to 0. So the net force in the Y direction equals MAY. There's no acceleration. They're going to add up to 0. Positive F spring 1, negative F spring 2 minus mg equals 0. There's my equation. So that's my force equation for this problem. What do we know? What are we looking for? We want to know delta X for the first spring, the top spring. That's hiding in here because we have, for spring forces, this equation. So we can use, anytime we have a spring in an equation, in a situation or a problem, we're going to use this one, I'm sure. So if I replace the F spring with K delta X, let's see what I get. So this is K delta X for spring 1. This will be K delta X for spring 2 minus mg equals 0. I'm looking for delta X1. I know K1. I know K2. I know delta X2. I know my mass. I know gravity. Got it. So I can just solve for delta X1. And I'm not going to bother doing that algebra. You can do that. You should get an answer for the stretch of spring 1 of 1.31 meters. So that is our answer. And now, is that reasonable? That's a pretty long way, because that's a meter, 1.3 is going to be like that. Okay, so yeah, I guess so. This one's stretched 40 centimeters, so that one's already stretched this much. And it is almost a 23-pound sculpture, so I would expect that it would stretch this quite a bit. And you can imagine that the top spring is likely to get much more of this, hold much more of the weight than the bottom spring. So I think it's reasonable. This is a pretty light spring on the bottom. This is a heavier duty spring, but compare that with the weight of this is about 95 newtons. So 95 newtons and 80 newtons per meter, I'm going to say that's reasonable. So that's a very simple spring force problem, but it had this little subtle point where springs can push on something, they can pull on something. In this case, we had two pulls, one in this direction, one in this direction. Another problem, if it had said spring 2 is compressed 40 centimeters, then if this one was being compressed, it would be exerting an upwards force on the sculpture, and this one would have swapped over. We'd have 2 up, 1 down. The sign of that would have changed. We'd have a different answer. If you want to try it and see what you get with that answer, that'd be a good way to practice. See what would happen if this had been compressed 40 centimeters instead of stretched 40 centimeters. All right, I think that is it. Good job.